Hey everyone, welcome to AstroPM. In this video tutorial, we're going to walk through some of our calculators. This one specifically, we're going to cover our sampling calculator, but we've got several others, exposure and focal length calculators. This section might grow as we add things to the software. So let's take a look, let's just dive in here at the sampling calculator. And this is a really popular tool. People are always looking to match up their camera with their telescope. And this makes it very easy to look at different combinations and to see really if that camera's pixel sizes are a good match for your seeing conditions and for your telescope. So the first thing you have to do is you have to make sure your equipment is set up. So it's really a camera telescope pairing, and so you want to make sure you come up here and set up your telescopes. You should have all this basic pertinent information in here. This optional data is just optional, but you should have at least the basics, and you can get this off of your telescope manufacturer's website. What is the aperture and focal length is really what's needed for most calculations. When we jump to the camera section, this section here is going to be pretty important as well. We need to have a lot of this information, particularly your pixel size, but it's helpful to have your sensor sizes, whether or not you can bin across all three modes, or maybe more, or maybe less. Maybe your camera doesn't do 3x3 binning, but it's nice to have some of this information in here. And we do have a camera library in here of a few basic cameras. But you're more than welcome to go ahead and hit the plus sign here and add your own camera specs specifically. So you need to have those two pieces of equipment set up. And let's jump down to our sampling calculator. And all we're going to do is we're going to try a couple combinations here. And I'll show you what some of this, how some of this data kind of works in and what you should be looking for. So I'm going to start out with just a basic telescope here, like a 8-inch Newtonian. Okay, this has a focal length of 900. It's an f4.5 scope, and down here below for cameras, I'm just going to go ahead and pick a ZWO 2600. This is just kind of a standard mid-size camera. You can see all the stats pull in here. Particularly, my pixel is 3.76 microns, and you can see my focal length is 900 up here. So let's jump out here and take a look at what it's doing. What we do is we can calculate the native 1:1, what is your image scale. Okay, and that's what this green line here is, just the native one. It's 0.862 arc seconds per pixel. So if you just take a camera, this camera at 3.76, and you put it in this scope, you're going to get that resolution. And so we all know, though, that in real conditions that is not maybe optimal or the best of what you can see. So there is another component here where seeing comes in to play. Now, what we do, and there's a bunch of stuff here I'll walk through, but we give you a couple of examples here. And you can see this dashed line is where you would be right now. If I click on 2x2 binning, that would put me out here. My image scale would now be 1.72 arc seconds per pixel. Okay, and if I drizzle, let's say I do a 2x drizzle, my resolution on my image would drop to 0.43 arc seconds per pixel. So it puts me outside of this green ideal zone. And the ideal zone is based off of a Nyquist formula, which is simply saying that 2 or 3 pixels is really a nice round star is what we're looking for. And so if we go back to this native 1:1, you can see this is a good pairing. Now, what's also being thrown into this formula for this range is your seeing conditions. And if we come up here to seeing, you can see I have 2 to 4 arc second seeing. It's going to use this lower limit. What is the best you can get? So you might look at your conditions and be like, oh man, I can't get 2 arc second seeing. I'm more like 3 arc second seeing. You'll notice that the scale moves out here. The ideal zone moves out. Your scale never changes. That's just basic optics, but your zone for which might be best gets worse and worse as the light spreads out across your image. The worse you get seeing, the more the light is pushed across more pixels. So if I have 4 arc seconds seeing to 5, you can see my ideal zone is way out here for this scope, and I'm going to be oversampled if I leave it at native 1:1. So if I click on 2:2 binning, you can see I'm now up in that ideal zone because it's based on my seeing. I don't have good seeing in this situation. I might as well go ahead and bin 2:2. I'm still ideal. I still get good round stars, and I also benefit by getting 4 times the signal on my image. So if we drop it, let's say we ship this same Newtonian, same camera, we ship it down to Chile and we get 1 arc second seeing, really good conditions. Well, that means that we're going to be, with this combination, a little oversampled. Even if I go back to native 1:1, this is what my scope handles, I'm going to be a little bit oversampled, or I mean, sorry, undersampled here. Okay, things are going to start looking a little bit blocky. My stars will be, and so this would be a situation where this scope could really benefit probably from drizzling. And you can do this on the software side and Pixin side or whatever when you're stacking, and you'll notice that your square blocky stars can become round through software processes. So doesn't mean your hardware is bad, it just means it's at its limit and you have really good seeing. So it's nice to see what this lower limit of your seeing and how it affects your telescope combination. Okay, if I'm in maybe some 2 arc second seeing, I can probably just leave it at 1:1 and I'm probably going to get really good round stars at this situation. So let's take a look at some other examples now of how this might play. Now let's say I have the same scope, but I switch it to a full frame camera from a 2600 to a 6200. What you would expect is nothing to happen because you're not changing the image sampling here, you're just adding more field of view to your system. It has the exact same size pixels, so nothing changes. We're just increasing our field of view. We're getting more sky, twice the imaging zone for the same camera. So switching cameras to a larger sensor doesn't matter if your pixels are the same size. Now let's switch to a different telescope. Let's go to a 14-inch RC. Okay, now if I go to a 14-inch RC scope and I have a full frame sensor, you'll notice that my pixel scale changes quite a bit. When I'm at a native 1:1, I can get down to 0.34 arc seconds per pixel. Okay, well, ideal conditions are way out here for 2 arc second seeing. Okay, I might be able to capture that if I dropped and had it at a really good site. Let's say I was in really good skies with 1 arc second seeing. I might be able to utilize that. But if I have, where I live, real bad skies, let's say 2 or 3 arc second seeing, I'm pushed way out to the right. So in this situation, it pays to bin. Okay, maybe I've got 2.5 arc second seeing or 2 arc second seeing. You can see I can just start to get into the good sampling zone if I bin at 2:2. I could probably even bin 3:3, but I think we're good here. And what you'll look for again when you look at your images, are you getting square stars? Are you getting nice round stars? It's always better to kind of be a little oversampled just because your stars are going to be round. You're just losing a little extra efficiency if you jump down into the oversampled zone. But when you're undersampled, you'll notice that they're very blocky, and you need to start drizzling at that point. So this is what the calculator will help you kind of decide, and it's kind of fun to play around with. Now, we also give you a couple of other calculators here. Sometimes you wonder which combination with this sensor, how big of filters do you need? So what we give you here is a simple calculator for filter size. Let's say your camera has a back focus like the 6200 of 17.5 or 12.5 if you remove the tilt plate on it, and you bolt, let's say, the a filter wheel to it. Your filters might be 22, 23, oops, not 223. Let's say they're 23 millimeters away from the sensor. So you kind of calculate your camera's back focus plus your filter wheel or whatever you have in front of your camera. A filter slider, a manual filter slider works. How far away are your filter? And this tells you you need at least a 47 millimeter filter. So you could probably get away with a 2-inch filter, mounted filter. Those are M48 minus maybe a millimeter for the casing, or you could get away with like 50 millimeter unmounted filters, and you have plenty of room across this full frame sensor. Okay, now let's switch it to an even faster scope. Let's go to something like a RASA 11, and you'll notice, hey, our filter size here does not cover it. I would need to go even 50 by 50 square wouldn't fit this, because the light cone is so steep on a f2 scope. This is a very fast RASA. So different scopes have different cones based on their effective focal ratio. So that's an important calculator. If I can move my filters a little bit closer, okay, let's say I get them down to 19 millimeters or even 17 millimeters, I can start to fit in a 50 millimeter filter on a RASA 11 and really cover a full frame sensor. Okay, if we switch a camera to, like, so let's say a smaller sensor size, now I can obviously cover it. I only need 36 millimeters to cover that. So much easier. So that's a kind of a neat little calculator if you're looking for filter size calculations. Okay. Let's take a look at some other stuff here. Again, let's look at this RASA 11, and let's look at a full frame camera, let's say. We'll take a look at this one. This one has 1.25 arc seconds pixel scale here. And so you can see it actually pairs up very well just in its native format. Okay, if we drizzle this, we might be able to, depending on our skies. So if you start to get really good skies, or you see a good evening of seeing, sometimes it could pay to drizzle. And if you have really, really bad skies, let's say you have 4 to 7 out here, this might pay to look at that, and maybe you could bend it and really get some more light. But that just depends on your seeing conditions. So this is just a basic graph, again, our sampling calculator of your pixel scale, but we throw in also what are your seeing conditions and what that might look like here. Okay, let's take a look at a couple more calculations. Right up here we have your CFZ. CFZ is your critical focus zone. How tight do you need to be in that really good focusing zone? Now, the faster the scope, the smaller that critical focus zone is. And I actually did two calculations here. One of them is just your critical focus zone, but the other one is with seeing. And if you have poor seeing conditions, you don't have to be quite as in focus, because the light's spread out across several pixels, and it's not nearly as intolerant of that focus. So the worse seeing you get, your critical focus zone sort of opens up a little bit, or relaxes, I guess is what I would say. You send the same scope down to Chile or to New Mexico with perfect seeing, your critical focus zone gets really tight, and that's pretty intuitive for most of us to understand that process. So this is a RASA 11 f2. Okay, that critical focus zone is 6 microns, so that's very small. Now if I throw in my seeing conditions, it opens up a little bit. Okay, it really might be 10 to 15, 20 microns in that range, because most of us have kind of normal seeing. So only if I ship it to a really good site would I start to see that 6 micron, 7 micron. I got to have perfect focus to get optimal quality. Okay, so that's what that does. Now if we go to a slower scope, let's say we slow down to a f6.7 scope, you can see how our critical focus zone is really much more relaxed, 55 microns. And if we throw in seeing, even good seeing, it's 100 microns. So it's very easy to hit focus in that zone with a slower scope. So just another calculation to kind of look at, gives you some good information, lets you kind of understand your equipment a little bit better. So hopefully that's helpful. That's kind of a long video on our sampling calculator, but there's a lot of really good information there that lets you kind of glean your scope and camera combinations. And it's fun to go ahead and experiment, put in different scopes in there. Maybe you want to look at what is a CDK 600 or a Delta Row 500. What does a $100,000 scope look like in terms of pixel scaling and cameras, and what can you run? And you can also play around with cameras. You can try some large pixel cameras. This camera here jumps up to 9 microns, and you can see how that really starts to pair well with a scope, how big pixels work on long focal length scopes. And it seems counterintuitive to most astrophotographers when they start working with imaging, but you can kind of use a calculator like this to start to understand how that equipment comes together. So again, if you have any questions, or you want to post something, post it on the video or send us an email. We'll see if we can help. Thanks for watching.